Thanks. Sorry, it wasn't me. So okay, so I'm going to talk about some work on controlling opinion bias. This is joint work with Chris Kuhlman and S.S. Ravi. And so here is the motivation for this work. And before I start, I want to explain the context. So my background is in algorithms and discrete dynamical systems, and we want to look at these problems from that context. And subsequently, we hope to enrich it with looking at more real phenomena. So for this audience, I don't need to motivate diffusion processes on graphs. So there's a huge variety of them for epidemics, influence, information, and so on. So there is a network, and it's something spreads on the network from one node to the other. So one class is like the stochastic, SIR, SIS, and variance. And then there are these threshold-based models. A person gets infected if enough of, like, let's say, majority of his or her neighbors get infected. And then there are these classes called voter models and so on. So our motivation is to look at phenomena such as like political leanings, which tend to be very polarized, like this visualization from Indiana University's Johan Bolen's group. So while it's very polarized, often there are these remarks that there is a large independent or middle which keeps switching. There are some small parts which are highly polarized or stubborn in some sense, but this middle keep going back and forth in terms of their states. And our motivation is to understand how this, to come up with models for this and look at interesting algorithmic questions that come out of this. So if you look at this kind of behavior, these models are not very well suited. Like threshold-based models tend to be monotone. Once a node switches from 0 to 1, it stays infected or it's in state 1. Variants have been proposed, like with competing diffusion processes, or a not pure threshold, not state 1 threshold model, where it can go back to 0 if not enough neighbors are in 1 and so on. But it's not clear whether they capture these aspects. So our focus is going to be on voter models. And here's a quick primer in case you're not very familiar with it. So we have a graph. And in this work, we'll treat it as we'll take a directed graph. Each node is in 2 states, red or blue. So red will be 0 and the blue would be 1. And so nodes are people, and this node is trying to figure out, it's in a blue state. It's trying to figure out whether it should switch to red or not. So the way it will do is it will look at its own, it will choose either its own state or the state of one of its neighbors randomly and switch. So this particular node is going to become red with probability 1/3, and every node does the same thing. And so from this configuration of red-blue assignments to the nodes, you get to this configuration with this probability and so on. So the nice thing in this setting is from this configuration, you can go back here or you can go to other configurations, for instance, this one. But the observation is these nodes can switch back and forth. So this does have the feature that we want. Unlike threshold models, nodes can switch from 0 to 1 and back and so on. So in general, we'll think of PVU as the probability that V adopts U state. It need not be uniform. It can be weighted and so on. And let FTV denote the state of node V at time t. So the voter model has this nice aspect that it allows repeated switching, and it has a huge literature. It's connected to random walks, so it's a good model to study. But one property which is actually a nice property and useful, and which makes it not so good for the setting we want to study, is that under very general conditions, these dynamics reach a consensus. So like very weak conditions like connectivity and so on. So basically it means if you run this model asymptotically, everyone will be will agree on the same state. So there are other extensions which have been proposed, and we'll study this by Yildiz et al. From a very recent model. What they say, they change the setting by saying, okay, so let's add some nodes which are stubborn in the sense that they do not change their states. So for instance, these two nodes with this added circle around, they only have a self loop, so they just stay at their own state. All the other nodes are like before. So if you look at this guy, he has outgoing edges into these two stubborn nodes, and so this guy is going to, in every step, he is going to switch his state with probability 1/3. Right? So in fact, in this kind of setting with stubborn nodes, there is no convergence to consensus in general. So this seems to have the characteristics that we would like. And so what I'm going to do in the first part of the talk is formulate some problems about how influence can be measured in such a network, and look at problems related to controlling it. So let V0 denote the set of nodes frozen in state 0. Again, red denotes 0 and blue denotes 1. V1 is the set of nodes frozen in state 1. So if you start from this configuration here, so 0, 1, 1, 0, 1, 1, 1, 0, this table gives the probability of being in state 1 in the next time step. So the next thing one can look at is at a given time, what is the fraction of nodes, the expected fraction of nodes which are in state 1. And so one can look at, so that's this average here. So note that it's possible that there can be a node which keeps switching its state 0, 1 every time, but the probability that it's going to be in state 1 is well defined, and so this quantity is well defined. So one can talk about in the next time step, what is the average fraction of nodes which are in state 1. So it's the average of these, and that turns out to be this number. So about a little more than half the nodes are in state 1 in this setting. So let's try to understand this a bit further before we formalize our problem. So let's take a slight difference in a slight variant of the same example. So now we have this node frozen in red or 0, and this node frozen in 1. Now we are interested in not just the opinion. So by the way, I'm defining the average opinion at time t as this average fraction. So now I'm going to extend this to asymptotics as t tends to infinity. So let f star denote the probability that a given node is in state 1 as t tends to infinity. So by a simple like Markov chain kind of analysis, you can write down the relationships for these probabilities, and it turns out for this example where this is frozen at 0, this is frozen at 1, this is the asymptotic probability. So this is of course in 1, this is 0. The color codes here tell you what fraction, what is the probability that it will be in 1. So U3 is it has a quarter probability of being in state 1, and so on. So if you look at the average opinion for this, it's this much, which is less than half. So in this setting, we'll say that the opinion is biased. So we'll think of half as being balanced, and our goal is to make it, our goal is to push it in one direction of greater than or equal to half. So in this example, this choice of freezing the node in state 1 is making it biased, it's less than half. Okay. So in this, can we modify this example by freezing a different node in state 1 so that we get the opinion to be more than half? And it's easy. If you freeze this node in state 1, then again you can write down a similar kind of thing and calculate the asymptotic probabilities that they would be in state 1, and it's quite clear from the color codes. So if you look at the opinion here, or the average fraction of nodes which are in state 1, that is half. And So we'll say in this setting, we are able to get the opinion at least to be greater than or equal to half, and so these are the situations we are interested in. Right? So if you define opinion in this form, it's either some fraction between 0 and 1. We are interested in settings where it can be made greater than 0.5. If it is less than 0.5, then we are calling it biased. And our general question is, given some nodes which are stubborn or frozen in 0, how many nodes we need to freeze in 1 so that this bias can be avoided. So let's just start with some examples of extreme cases where this quantity is either small or less, and that gives some idea of what things to look for. So first, consider this example of a star graph. If you freeze the central node in red or 0, then clearly every leaf which is not frozen, which is independent, will end up becoming red. Right? So in order to, in this example, in order to get at least half the nodes in state in red or sorry, in blue or 1, we will need to necessarily pick 3 leaves and turn them blue or freeze them in blue. Right? So for this choice of this configuration with the star center frozen in 0, one needs a lot of nodes to be frozen in 1 to get over the 0.5. And one can generalize this example and construct instances where you need as much as the maximum degree to get opinion over 0.5 in general. The problem is this is a very, the degrees are very skewed. The other extreme is complete graph. It's very well mixed. So if this node is frozen in 0, this node is frozen in 1, it's very clear that for every other node, there's a half probability in being in state 1, and so if just by freezing one node in state 1, any one of them, one gets opinion equal to half. Right? So our motivating question is going to be, given a set of nodes frozen in 0, how many need to be frozen at 1 to get an average opinion more than half? And so again, like I said before, we'll call that the problem of countering bias. So let me formulate these problems a bit more. Again, bias means being in state 0. So the first set of problems we'll look at is, we call this the minimum opinion control set. So given a set V0, so we're given a graph, we're given this V0, and we're given this parameter epsilon. The goal is to choose the smallest set V1 such that the opinion at some time t becomes more than epsilon. Generally, we deal with epsilon half, and so we'll call this MOCS at time t. And there's an asymptotic version where we are interested in the opinion as t tends to infinity, and so that's just the MOCS. So with this kind of quantity, we are dealing with a specific V0, and it might be hard to compare across networks. So we'll normalize it by this minimum opinion control factor problem, or MOCF. So here we are given a parameter k, which is how many nodes can be frozen in 0 initially, and we look at the max overall choices of V0 of the MOCS divided by the size of V0. Okay, so again, low MOCF implies it's easy to counter bias, formulated in this sense. And the goal is to understand these quantities computationally, and from a dynamical systems point of view, develop techniques to estimate them and understand them in real graphs, whether it's small or large. So one very useful thing in the computations and the analysis is this dual view of coalescing random walks, which has been developed in the context of the pure voter model, and it turns out it holds here as well. So, so we have, this is our graph. These are our stubborn nodes in red and blue. And now if we look at this node, we want to find out what is the probability that it will end up being read asymptotically, let's say. So that can be viewed by a different process. Do a random walk starting at V, and ask the following question: what is the probability that this random walk will end up at this node and not this node? Right? And it turns out, one can show this by induction, that this probability is exactly the probability this node will adopt the state 0. And so once we prove this, this gives a simple Monte Carlo scheme to estimate this average opinion. One can just start a number of random walks and look at the fraction which are in state 1. So let me summarize our results. So our first interest was to see how this quantity looks in many different graphs. So we look at 14 different networks, that publicly available networks that we chose to have different applications, different variations in their clustering, degree sequence, and so on. And we find, first of all, this MOCF can be quite varied. It can be quite large in some of the real networks. So for instance, we consider a few networks which involve influence and information spread. So like a Twitter retweet network and the wiki network, which was talked about last several days. So it tends to be, empirically we find, it tends to be higher in those than in a collaboration network, like the co-authorship graphs of condensed matter papers and so on. Again, in our experiments, we consider the static graph. By now we know that the graphs and dynamics co-evolve. So I mean, the next step would be to look at this in a dynamic setting. But these results are all for static graphs. The other thing we find, again, which is consistent with the example of the star versus the complete graph, it increases with the heterogeneity in the graph. We, in addition to support our the empirical observations, we wanted to look at analytically, can we say something about it in some random graph classes. And so there is this model by Chung Lu, which is the multiplicative model. So you're given weights on nodes, and you put in an edge with probability proportional to the weights. And we find that there is an interesting dichotomy in terms of the MOCF value in this model. If the power law exponent, so we are assuming the weights come from a power law. If the power law exponent is greater than 2, then the MOCF is a constant. But if the power law exponent is less than 2, then it can be really large. And then complexity wise, these problems tend to be really hard. We also look at another variant. So I'm skipping many of the results in interest of time to be able to get to some of the empirical results. So we also look at a variant of this process in which we allow the nodes which are frozen in 1 to be able to spread through an independent cascade. So again, this is our graph. These are the nodes. This is the set V0. Now let's say we freeze this node in state 1, and we consider an independent cascade model which with very low probability that can spread this diffusion to its neighbors and subsequently. We are interested in seeing how this affects the diffusion, and we find that even very low transmission probabilities for this can reduce the MOCF quite a bit. So okay, so let me speak fast and go over some plots. Okay, so this is a summary of the different graphs that we consider, and maybe if I do stop, I'll probably go over this. So this has a lot of lines. So what is being shown here is the average opinion in two different graphs. This is a Twitter retweet graph that was using political hashtags that we got from Johan Bolen's site. And this is a collaboration network, the co-authorship network for condensed matter physics. And what is being, each curve shows a specific value of V0. And on the x-axis, we have the size of V1. It's chosen in this case randomly, in this case based on degree. So what we find in the in this co-authorship network is the y-axis is the average opinion. As we increase the size of V1, of course, the opinion is going to go up. But in the co-authorship network, it doesn't require too much of, it doesn't require a large V1 size to get above the opinion of half. But it seems to be much different in the Twitter graph. One needs quite a bit to get to this threshold of half. And we find if you look at the ratio, it turns out to be, in Twitter, it turns out to be more like a factor of 5. Let me just get to the summary. We tried, so the thing on Twitter seemed to be similar in other influence kind of graphs, opinions, and so on. Understanding why that's happening would be a good thing. I'd like to say that maybe scientists are less biased, so I don't know. So the other obvious thing is, so the voter models are very strongly connected, or they can be analyzed by their spectral properties. And that's the next thing to examine more carefully. We haven't been able to use them very much in terms of helping with the algorithms. Other extensions of voter models would be useful, would be interesting to study. One which might be, instead of having a stubborn node, thinking of making each successive switch harder to capture some kind of inertia would be an interesting thing. And the final thing would be to look at dynamics and seeing how this can be used in more real settings. So thanks.
Thank you very much. One question.